So as we start chapter 11, we're going to go back to something we talked about in the first part of, I guess really it was in Math for Business 1 when we talked about all those interest formulas, if you remember, if you took that course. If not, you probably talked about interest formulas in college algebra. And one of the more common formulas that would be used for calculating interest is for continuous compound interest, and it involves the number e. Now, e can be defined this way. It is finding the limit as n approaches infinity. So as something gets more frequent or gets bigger and bigger and bigger, and what we're finding the limit of is 1 plus 1 over n raised to the nth power, okay? You could also write it this other way. And basically, once we calculate that limit, what we find is e is actually a number, much like pi is. We know pi is about 3.14, da-da-da-da-da. E is a number that is 2.7 something, okay? And it is a number that just occurs naturally very often. We find it in the science field, in the natural world. And then, as I said, we use this a lot in a business sense because there are a lot of things that will involve this number e. But that's how, right here, is how e can be calculated. All right, and if you use your calculator, scientific or a graphing calculator is going to have a button for e. And you will be able to see that decimal approximate, just like pi, you can not, it is irrational. It is not a decimal number that ends or repeats. The same is true for e. It's an irrational number, but we can get a decimal approximation for it. So, if we wanted to simply evaluate something that involves e, such as this one right here, a equals 500 times e raised to the 0.03 t power, and then they're going to give us some different values for t. This would give us a final amount using this interest formula. If you, say, invested $500 at 3% interest for, if we use t equals 3, that would mean for 3 years. That would be exactly what we're finding. So let's make sure we don't have any trouble with calculator entry. Before we start, let me just give you a quick reminder. If it's been a while since you have talked about this formula, the A stands for the final amount, or your ending amount. So make sure you realize when they give you values and you have to plug it in, that you know, is this a beginning amount or an ending amount? Ending amounts will be A. That means your P is your beginning or your starting amount. And the R, you guys can probably tell me, is what? Yes, your interest rate. And T is time, but you've got to make sure that it's always expressed in what? Years. Very good. So if you were putting something in for 6 months, you would need to use what for T? 0.5 or 1/2. Very good. All right, so on this one, if you were looking for this ending amount, if you put in $500 at 3% interest for 3 years, make sure if you put that in your calculator that you're getting the right answer. What are you going to come up with? $547 and what? Give me 3 decimals to the right. 0.0 what? 0.087 is going to round to 0.09, right? To the nearest penny. Yeah, we want to round to the nearest penny. So that's 2 places to the right of the decimal. All right. If we then put in 6, let's say we leave it there for 6 years, we would get what? $598 and 61 cents. Very good. Okay, so 3 more years yields us just a little more than 40 extra dollars. That's not necessarily a big return on your investment. Let's see what happens after 9 years. 500 times e raised to the 0.03 times 9 power is
654, actually 655, because it's 98.
so rounded to the nearest cent, 654.98. Okay, so we increased a little over $100 extra for those additional 6 years. If you compare the amount you would have after 3 years to the amount you would have after 9 years, you've earned over $100 in interest. Okay, so just plugging in, being able to put it directly into a calculator, we're good with that, right? All right, let's look at what we have here is an equation that has e in it that we're now solving for t. The issue is t is in the exponent. Now, this is where knowing something about logarithms is really important. Do you remember what is a logarithm? We have log logarithms and we have ln logarithms. An log logarithm means that you're using base 10 unless they give you a different number for the base. An ln means that the base is e. So let me give you a quick reminder of what hopefully you have looked at some point before. Let's say I asked you if you had 5 raised to some power and that was equal to 25. Can you tell me what x would have to be to make that true? What would that exponent have to be in order for this to be a true equation? Exactly. Now we know that because we understand that if I take 5 and I square it, I get 25, right? The problem is, what if this had been 5 to the x power equals 31? No idea, right? I know it's got to be more than 2. It's definitely less than 3. And we need a tool for being able to find it because we can't always just look at it and see. Now let me show you what the tool is. This is where the logarithm comes in. A log simply allows you to solve for an exponent. That's all it is. It's a tool for solving for an exponent. And if we went back and we spent a little more time talking about it, what I would try to explain to you is that logarithms and exponents are inverse functions. Inverse functions happen when you switch x's and y's, and the problem is if you have your y in the exponent, the part you're looking for, we don't really have a way of solving it unless we do this. If we remember in algebra, that cardinal rule is what thou doest to one side of an equation, thou must doest also to the other. So it's perfectly legal to take the log of both sides. Now, there are some rules for working with logarithms. Let's see if you guys remember them. If I'm taking the log of something and there is an exponent after it, since a log is an exponent, okay, if I want to know what the log of 5 is, I'm saying what is the exponent? 10 has to be raised to give me back an answer of 5 because I'm solving for the exponent. So in a sense, anytime I see log, it means this is an exponent raised to an exponent. If I have a power raised to a power, what am I supposed to do with the exponents? Like if I had x to the third and I squared it. If I had x to the third and I squared it, what would that equal? What do my laws of exponents tell me I can do with these? Yes, exponents are multiplied together if I have one base with 2 exponents. That's the same thing as x to the 3 times 2 or 6th power. So think of it this way. I have an exponent raised to a power. I multiply those together. Here's how I'm going to do that. This x that's my exponent, is going to pull down in front of the log, and you get x times log 5 equals log 25. Okay? So what I'm trying to do is just show you the basic manipulation of how these logarithms work. Could I get x by itself now? If I do what? Divide by log 5. Because again, as long as I'm doing the same thing to both sides. So if I divide both sides by log 5, I now have something I can put in my calculator. You got your calculators? Pull them out, and here's what I want you to type in. Hit the log button, the log button. It should open up a parentheses. So you're going to hit log, type in 25. Now close the parentheses because we're through with the numerator. Hit division, divided by, and then type in log 5 and hit enter. What does it tell you that x equals? And we knew that, didn't we, before we started, simply because we had numbers that were easy to work with. The problem is, if it had been something like 31 over here instead of 25, I can't just look at it and figure it out, but I could find it, a decimal approximation for it, by doing this, okay? So we're going to apply this procedure to a problem like this when I see that the variable I need to find is in the exponent, okay? Now, what I want to pay attention to is my base, because if my base is a number like 5, on this example that I just showed you, I can either use log or I can use ln. It doesn't matter as long as I'm taking the same kind of log on both sides. I either had to do the log of both sides like we just did here, or if I wanted to do the ln of both sides, I could have. In fact, it might be helpful for you if you see this in your calculator instead of using the log button. See what would have happened if you'd used ln. I want you to do ln of 25, close your parentheses, divided by ln of 5. You got the same thing. It doesn't matter whether I'm using the log or the ln if it's a number that's there. But if the number is e, if that's my base, I definitely want to use the ln. And the reason I definitely want to use the ln is because ln already has e as its understood base. And there's a little shortcut. Again, if you haven't done this in a while, or maybe you haven't done it before, let me explain this to you. Suppose this had been what we were trying to find. Let's say we wanted to know e raised to what power would be equal to let me think. How can I, okay. Let's just say e raised to what power equals 1. Okay? Now, instead of doing the log of each side, I want to do the ln. And the reason I want to do the ln is because the base is understood to be e. Okay? We don't write it down because we already know that it's e. It's sort of like in a square root. You don't put a 2 as the index when you write it down. It's understood to be 2 unless you write something else. So if you just see ln, the base is understood to be e. Now, think about what this means. This is asking you, anytime you see ln or log, it means you're looking for an exponent. So this is asking you to find the exponent that e has to be raised to give you an answer of e to the x. Okay, now don't get lost in the words, but think about that for a minute. I'm looking for the exponent that e has to be raised to give me an answer of e to the x. What is my exponent?
X.
It's x. You could think about it this way too. If you do what we did a minute ago, you could bring down the x so that you would have x times the natural log of e. And anytime this base matches what follows it, when it's in log form, the answer will always be your exponent. It has to be. If this base is the same, I'm looking for the exponent that this base has to be raised to give me this. Well, it's got to be whatever that exponent is. So that's where we get a little bit of a shortcut if we see we have an e. I can take the natural log of each side. So if I take the natural log of 4 and set it equal to the natural log of e to the 0.07t power, okay, what can I do on the right side? How can I clean up the natural log of e raised to the 0.07t power? It's just going to be the exponent because I'm looking for the exponent e has to be raised to give me e raised to the 0.07t power. That's got to be whatever that exponent was, 0.07t. That's the tool that will be really helpful if you see that your base is e and you're looking for a variable in the exponent. Okay, if I were to ask, how many of you say, okay, I kind of remember doing this at some point in the past? All right, I'm seeing most hands here. We can spend a little more time on it if you need some extra help. Now that I've taken care of getting the t out of the exponent, all I have to do to solve this is what? Solve for t by, there you go, divide both sides by 0.07. And that gives me something, I can go to my calculator. Don't expect it to be an exact value. It's probably going to need to be something rounded. Most of the time when we're working with these, it will be. And it said solve for 2 decimal places. So I want to see if you can put that in your calculator correctly. Tell me what t needs to be rounded 2 places to the right. Yes, if you put it in your calculator, you're going to get 19.80. You need that 0 in that last place because it identifies you rounded this answer. If you only write it as 19.8 and it told you to write it to 2 decimal places, that makes it appear that it came out to be exactly 19.8 and this one didn't. Okay? So if you look at the next example, I'm solving 3 equals e raised to the 4r power. What's going to be the little handy tool that lets me solve for an exponent? I have to do what? I'm going to take the natural log of both sides, right? So I'm going to take the natural log of 3 and set it equal to the natural log of e raised to the 4r power. Which side can I clean up now? The right side, because if I'm taking the natural log of e to a power, then it just cleans up to be what?
14.
Yeah, whatever that exponent is. So it's going to be 4r, and to finish solving for r, divide both sides by 4. Now if you put that in your calculator and you round 2 places to the right of the decimal, r is about what? 0.27. Good job. Okay, so that's the basic concept we're going to be working with here. Look at number 4. Bank A offers a 5-year CD that earns 1.75% compounded continuously. If you put $5,000 in it, what's it going to be worth in 5 years? I don't know why they wrote all these problems with such tiny interest rates. It doesn't encourage you to want to save if you're looking at it with a tiny interest rate. First thing I'd say is shop around, find you a different one. And when I get ready to plug this into my formula, A equals PERT, principal times e raised to the RT power, I need to make sure I know what all these pieces are that have to get plugged in. Now the first thing that I'm noticing is I need the e, A equals PE to the RT power, because it said compounded continuously. If it had said compounded monthly or compounded quarterly, that's a different formula. But we're working with compounded continuously in this section. And that means this 1.75% is going to go in as which letter in my formula? My R. And R is going to need to be written how? As a decimal. So make it point what? Excellent. 0.0175 is my R. Now, I look at the next part and I see the number 5,000. Is that an A or is that a P? That's my P, isn't it? Because that's how much I'm investing. That's my beginning amount. I'm going to solve for my A, so I'll know how much it's worth in 5 years. So 5,000 goes in for P times E raised to the 0.0175. What's my T? 5. Well, you know what? This is just like the first example we did. We don't have a variable in the exponent. We were able to plug everything in on the right side. We're solving for A. See if you can tell me in 5 years how much has your $5,000 grown. That's it, $5,457.21. Now the next one is kind of interesting because now we're going to figure out how long it would take for the account to be worth $10,000. Okay, I still need A equals PERT, and my interest rate is still my 0.0175. I hope you've got a lot of time because I think it's going to take a while to get there. But let's see if we could figure out how to plug into our formula to find this. Do I know what my A is now? Yes, because I want it to turn into $10,000. So I'm going to put $10,000 in for A. I'm still starting with the $5,000 though. I still have the same interest rate, which is 0.0175. Yes, I am trying to find the T. How am I going to do that? Excellent. Before I try to take the natural log of each side, I need to have the only thing on the right side be e to that power. So the first thing I want to do is divide both sides by 5,000. And fortunately, 10,000 divided by 5,000 is pretty easy to work with. That's 2 equals e to the 0.0175 t power. And now we can do what to both sides? Take the natural log. Excellent. Okay, so I'm going to let you guys figure this out in your calculator. See if you remember where to go from here. And in just a second, you are going to tell me how many years this would take. So once you took care of the natural log of each side, you should have put the natural log of 2 divided by 0.0175 in your calculator, and that gave you a t value of what? How many years?
If it's a decimal, do you go up to the next year?
Well, let's go ahead, since they had asked us to round to 2 decimal places, let's go ahead and do that here. So if you were going to leave 2 places to the right of the decimal, you get what number?
39.61.
39.61 years. You better be very patient.
39, isn't it?
Yeah, at 1.75% interest, it's going to take you almost 40 years to double your money. Okay, because that's really what we're, yeah, that is not good. You want to get a much better interest rate than that. So yeah, if you change that to a number that's more reasonable, you can, I mean, a lot of times you can double your money in somewhere between 5 and 10 years. That's a good investment, all right? 40 years, not so much. How about this? A couple paid $30,000 for a house 40 years ago. Today, they sold the house for $250,000. Now, it sounds like, what a deal, right? If interest is compounded continuously, let's see if we can figure out the nominal rate of interest that $30,000 earned. In other words, let's see how much return they got on their investment. So, can I use A equals PERT here? Do I need something different? When it says compounded continuously, then I can use A equals PERT. Okay, so we're just, I mean, it may not be that's the way that their mortgage was set up. Most of the time, mortgages are not interest compounded continuously. But this would just give us an idea of what interest they earned. What goes in for A? Yeah, 250,000. P is 30,000. Times e to the, do I know r or is that what I'm finding? That's what I'm finding. And what goes in for T? How many years ago did they buy the house? 40. Lived there a long time, didn't they? Okay, what do we do now? Divide both sides by 30,000. And if we do that, we come up with something like 8.3 repeating. Very good. Equals e raised to the 40r power. Now you do what? Take the natural log of each side, which means I have 40r on the right equals the natural log of 8.3 repeating. So if we divide both sides by 40, we'll get our answer. Let's see what their, and remember our interest rate will be in decimal form. So what was their nominal interest rate? 0.053, which is 5.3%. Okay, I mean, that's not a barn burner, but that's a heck of a lot better than 1.75. Okay, so give you a little bit of an idea. Now, here's one that is helpful just to see what kind of rate you would need to have if you want your money to double in 10 years. Okay, so if you look at this, the fact that it's compounded continuously is my clue that I still need A equals PERT. But they didn't give me a beginning amount or an ending amount. What did they tell me? I want it to double. That means I can pick anything I want and double it. What would be the easiest number to work with to double? Exactly. Let's figure out how long it would take $1 to turn into 2. So if I want $2, but I'm investing $1, I want to know what interest rate I need for it to double in how many years? 10. Okay. So if 2 is equal to e to the 10r power, when you take the natural log of each side, and we know we're doing that because of that base of e, we're going to come up with 10r equals the natural log of 2. Can you tell me how many, or what is going to be the interest rate you need? 0.069, or pretty close to about 7%. Which if you're investing wisely, you kind of shop around as long as you're comfortable not having it in the bank. I mean, sometimes it can still be accessible if you need it. Other times you may be putting in something that it makes it a little harder to get to, but you can definitely get a better interest rate, something similar to this.